Hi everyone, thanks for joining. Let's code an LSTM on some Yelp reviews. This video is going to go over basic data processing and the theory behind these models, particularly into word embeddings and how they can be actually used to identify similarities between different words or even different documents. We're also going to go into a little bit of the math behind LSTMs. Part 2 is going to actually go over coding these LSTMs in PyTorch, but right now we're going to focus on preparing the data and get everything set up for the experiment, so let's go ahead and get started. So this is actually from a Yelp research data set, which you can download in the link in the description below. But this idea is they released this really large data set of different reviews, and we're going to go ahead and just grab these reviews. And so one of the files that we're going to look at is this review.json. So we'll go ahead and take a look at it now. So once you download the data, the first thing I usually like to do is using a editor like Ubuntu in Windows or PowerShell in Windows, or you can just use a terminal in Mac. Is actually navigating to the folder and then actually just using the directory tools to check it out. The reason I like doing this in sort of this terminal and not in Python terminal is just because if I do this on the Ubuntu or on a PowerShell and terminal, then it's a lot faster. And that even if I have a really massive data set of 100 million files, I can still end up loading this and checking out what this looks like pretty quickly. So just as an example, this is we'll just say more academic data set here. And these commands should work with really any of these. So we see that we have each line will indicate a different JSON file. We have like a review, a user ID, a business ID, the number of stars, if they're useful, cool text. So maybe I can try to zoom in a little bit here. But essentially, it looks like, yeah, we're kind of most interested in, let's see, I think we want business ID because, so one thing I did notice about this data set is that there are, only so many, there's like 200,000 businesses and 8 million reviews. So when we do our training testing splits, we need to make sure that our training data is actually independent from our testing data. So we need to split on the basis of business ID, not the individual review. And I think this is pretty important because you'll get really biased error results if I just naively split on the review instead of on the actual businesses. So we'll keep that in mind for next time. We also have like stars. So we're going to need the stars, I think the business ID, and then it looks like this text column. Is it just called text? Yeah, it's just called text. So we'll go ahead and look at how to do this in Python now. So let's actually take a look at our data in Python. So we can just start by saying import JSON, and because you didn't need to necessarily look at it using the PowerShell or the Ubuntu or terminal like I had done before just now. But it did give us kind of a better idea of how to really interpret it, because I'm just going to treat it like each line is a JSON object, essentially exactly what it is. So we can just define some empty list as data here. We can say using data, we can say with open the name of the file, Yelp academic review as file, and then for every line in that file, for every line in that file, we can append to our list the JSON load. So we want to load this as a JSON file. This should be a line. So yeah, I should have said JSON loads the line and not the file. So yeah, essentially we have the JSON object where we have an empty list. And then we're going to open this file as file. For every line in that file, we'll append JSON loads. This is actually how you can do a lot of these sort of review data sets if they come like JSON files. So it's going to take a little bit to load. We'll come back when this is done. So now that we've looked at the data, let's look at what we actually can do with these reviews. So these reviews range from 1 to 5 stars. And we're just kind of do the most simple task we can think of. We're just going to predict the star rating from each individual review. And so we actually do have a little bit of a problem here, because if we're trying to make this like a sentiment analysis classifier to essentially predict positive or negative, what we should do with sort of the neutral reviews kind of becomes an issue, because you don't really want to train anything on nothing that you don't want to like train any neural network or any real model on something that you're not very confident in necessarily the result. And this idea of these neutral kind of reviews aren't really indicative of anything. They're kind of just, not really that informative. And so if we're really trying to make a review that's, in the real world, what you would think about is you would make this sort of algorithm in order to make a single binary decision. Should we do it or not do it or something like that? So in that case, it usually makes more sense to just kind of train on only the things you're certain of. So that's what we're going to go ahead and do here. We're just going to pull out everything that's at or below 2 stars and call that a negative review, or everything that is at or above 4 stars, call that a positive review. Then we're just going to throw away everything that's not really in those in between those two. So let's go ahead and do that now. So now that it's loaded, we can just go ahead and take a look. So if we just return, one of these objects, we have a review, a user ID, everything that we saw in the previous example. In order to, each one of these is a JSON object. So we just would say, to get the text, you would just say text. That's the text. And then we would just say, stars. And then what's the last one we need? Business ID. So let's go ahead and get each of these. So we'll just say BID. And this is just kind of more or less basic Python. But we're just going to define some business ID list. We're going to define some stars. And I bet there's probably a much better, a more efficient way to do this. But I'm kind of lazy. I would rather just have something run and maybe take a while than actually spend like a lot of time optimizing it for it to run super quick. I'd rather just, leave it running and go cook some dinner or something. But I'm sure if you're a computer scientist, you could make this a lot easier. Maybe probably even if you aren't. But this will hopefully just be very transparent and be able to see. So essentially what we're doing is we're just going to append to each of these lists. But we also want to check the condition. Remember, so we really we want to only pull the positive or the negative reviews out. So we don't want all the reviews. It's not really informative. So we'll say something like, we'll say star equals data should just be stars. Is it stars or I think it is stars. So then if star is greater than or equal to 4.0, then sure, then I'll BID append, and I'll just copy and paste this here. So it's essentially I'm asking the question. I shouldn't have done this. I shouldn't have run that. It's no big deal. I can just rerun that. But essentially I'm going to ask the question of if it's above. If it's above 4 stars, so if it's 4 stars, 4.5 stars, or 5 stars, I'm going to pin the business ID. I'm just going to pin to 1 to be a positive label, and then I'll pin the text as well. And so this will just be text. And I'll just do the same thing if it is lower than 2. So this way, we're only pulling out the positive ones, and we'll, of course, append a 0. So now if you look at this, it should work. I'm checking the stars. If the number of stars is above or equal to 4, or if it's less than or equal to 2, I'll go ahead and keep them. So we'll let this run for a second. So just as a double check, we're gonna just see how long each of these are. These all should be the same length. So business ID looks like 7 million. So it's pretty good. We still got quite a bit even after removing some of the more neutral stars. Cool. So all these are the same length. So everything looks good here. So if we just want to, let's go ahead and just take a look at some of these dismal, lukewarm systems. They didn't really enjoy this, I suppose. So this should be, what do we have? Stars should be like 0. Yeah. So it's pretty nice. So I guess it worked out. We were able to successfully extract these. So let's go look a little bit more in depth into how these are really structured using word vectors. So now that we've actually cleaned all of our data, we can actually start thinking about what we're going to do with this LSTM and actually making this classifier. So what we need to do right now in the rest of this video is we're going to prepare this data for the LSTM. That's going to involve tokenizing the text. We're also going to do some visualization of the word embeddings and take a look at those, and we'll go through a little bit of the math behind LSTM. one of the first things we need to do to prepare our data for our neural network is we actually need to tokenize and remove the stop words from this text. So we'll go ahead and take an example of this kind of string, I am Sam, I like ham. If you just think about what a tokenization method would be, essentially just splitting these up into different characters, into subsequent tokens. So now this is just 6 different tokens instead of a sentence. We understand that there is some kind of sequential structure to that. We'll talk a little bit more about how LSTM will actually incorporate the fact that I comes before am and that comes before Sam and all that. And the other thing we're going to do is actually remove the stop words. And so these stop words are just a word that they kind of use for sort of common English words, and they kind of just remove these. They tend to not be very informative for a lot of tasks, and so sometimes the model actually is improved once we remove these stop words. So we'll go ahead and do that as well. So what we need to do is feed a raw text into these neural networks and somehow represent this numerically. And this is what actually word embeddings do. And so these word embeddings are just essentially learned representations of words that are trained based on other models which are trained to predict the context of a given word. So they're trained on a large amount of data. Usually you can have something from Wikipedia or Twitter or PubMed or some kind of financial statement. So there's a lot of special dictionaries. So I definitely recommend if you're doing something in a given field and you're trying to do some kind of classification, sentiment analysis, you really should look into using word embeddings that are trained on the same sort of data that you're looking to apply it to. But this idea is that they essentially learn for each word a vector representation that is some numerical representation that represents the context of each given word. And the fact that these kind of end up being vectors give them a lot of very interesting properties. And one of the properties that vectors have is that you can just add vectors together, and you can also compare vectors to find their distance from each other, and that's what it's using cosine similarity. And so if you recall, not only can we represent words as given vectors, but we can also represent entire documents as a given vector. And this is just the average. This kind of goes into the additive nature of these vectors. We can just add them together and find the average vector that represents this document. And so this can actually be used a lot for recommender systems or kind of recommendation systems or finding similar documents to each other. If you're doing some kind of task like that, you could really just use something as simple as just using the cosine similarity of the average word vectors for a good word embedding dictionary that you found. And using this will actually help you find the distance. So if you recall just some basic sort of math here, if two vectors are lying on top of each other, the cosine of that angle is going to be 1. Essentially, so that's the maximum. So this sort of cosine of theta is maximized at 1 when they're right on top of each other, and all the cosine of this angle, the angle between those two vectors represents sort of this similarity measure. And so vectors that are closer together have a higher similarity than vectors that are further together. And so we see things like clustering by genre, for example, for given documents, or clustering by similar words. And we're going to go into our reviews right now and actually see how some of these embeddings look and check out some of the relationship that these word embeddings are able to give us. So now we're going to actually look at using some preprocessing and taking a look at the word vectors and some similarity measures with our data. So as we recall, we had our 3 different lists that contain the text of the reviews, the number of stars are essentially positive, 0 or 1, positive or negative, and the business ID. And so now we're going to import these 2 packages. I have some installation instructions in the code below, but this is just Spacey and NLTK. Both of these are pretty good packages for NLP work in general. They have a lot of really powerful tools. And so what we do is we're going to use the NLP model. We're going to say our NLP is equal to Spacey load, and then we'll go ahead and choose whichever one we downloaded. Because we want the word vectors, we're going to use the larger one. If you don't want to use all the room, you could just use the smaller one. Either one is fine. And so we have it here. So we're loading that as our NLP model. So it might take a second. While that's running, we can also, so the way that this works is essentially we'll be able to call this function NLP, and we'll be able to say, on any given review, let's say if we have the 33rd review, and we just want to look at the text, it'll actually, so now it'll just return this text of this sort of NLP model. And this is actually really kind of nice and convenient, and we'll show a little bit more. So the first thing we actually want to do now, though, is actually remove these stop words. And so before we want to, for each of these NLP models, we want to remove the stop word. So we're going to say, so if we want to take a look at the stop words, I think it's the command is something like this. So the stop words are, you see the different one that's like I, me, myself, and ours. And so you can use these stop words. So we'll take a look at how to actually remove these from the text right now. So what we're going to do is we're just going to use that same list of stop words. Is we're going to just call that into a single variable called stop words. And then what we can do is we're just going to essentially loop over every single thing. Well, we actually need to call this a document first. So we're going to use this NLP object. We're going to call that some document here. And so now if we recall, we just have this NLP object document, and we have our stop words list. And so in order to just remove these, it's just more just pretty basic Python. So it's like for text in document, you have to do really this or something like you have to do print text because that's actually to get it to be the token. So we can say if text So we'll do it like this. So we'll essentially just say if the token text is not in the stop words list, then we'll append that to another list. And you can see how we'll just do these for each of the I think we really need to stop this so we can rerun it. I think it's being a little efficient. So no stop. So essentially, yeah, we're just going to define an empty list. For every token in this document, we're gonna see if that text is in stop words, and if it is not in there, then we're gonna append it. So that's our way of removing stop words. So we'll run that, and we'll come back when this is done. And so now, if you just see, so after that ran, we just see if we run no stop. Essentially, we get the same list except without any of the stops, without any of the stop words. So we can do this, with any another review, and we get a different one without. Stop. So what I want to talk about next is actually using the NLP tool and Spacey to actually compute similarity between two different documents. So say we had this document, we'll have document 1 and then document 2. So these will just be different documents. So we want to figure out the similarity of these documents. So let's go ahead and take a look. So document 1. So wonderful nail shop. Eric is the owner, so hospitable, and I take his time and your effort on your nails to perfect them. I love my nails. They're so cute and symmetrical. Well, so then next, we have another one. Who knew? I did. I remember that meeting eating times in the early childhood days back in Chipotle and Denver. All right, so these are kind of different, but we want to figure out really how different they are. So actually, using the whole document, we can use this just a function and to find the document from document 2. What's the similarity to document 1? It's as easy as that, and we get some number here. So we could do something like actually computing the similarities. Again, this is really helpful for determining, having a document, what are similar documents to that. So you don't even necessarily need to do an LSTM for some tasks. And something like this might be actually a really useful and really powerful way to take advantage of a large amount of data. And finally, I just really want to demonstrate really so that so you really if you recall, each of these are document. Each of these documents are now represented as a vector. The length of this document vector is going to be 300, or they have different ones that are 200 or 100 or whatever. But it's the same as each of the individual words. So if I just return these vectors, the documents, we get 300 different numbers. The same thing happens if I take an individual word. So if I say doc1 for token in doc1, I want to see print token. I'll say the length of token vector. And so this is now the word vectors for each of these individual words. And so each of these words, as it's going to be here, have a given word vector representation. This is a wonderful nail salon. So this is and these are each 300 units long. So I think it's just really important to understand that these are vectors, and so this is actually how we're going to feed this into our LSTM next time. Okay, so now that we finally have our vectors, we need to think about kind of an intelligent way to sort of combine them. And for certain sort of tasks like similarity measures, it does actually end up being very useful and very kind of a good way to go is just by averaging the individual word vectors and to get some document vector and then comparing those. But when you think about doing something like classification, you actually want to really think about the fact that you have a bunch of word vectors and they have some sort of time structure to them. We understand kind of language and sentences, you read them right from left, or in other languages, left to right. In other languages, you read them right from left, but you have some sort of structure that you kind of read. And so we want to really understand these word vectors as a time series. So how do we actually analyze that? And that's through a method called LSTM. And so LSTM is really sort of a notoriously difficult topic to teach because it tends to be very complicated. If you've been looking up at this topic, you've probably seen a lot of people use this sort of depiction and these pictures, and I actually don't find the pictures very intuitive. So I think for me the easiest way I actually understood this was by looking at the math. And so if you look at the math here, essentially you just have to think about what are the parameters that go into an LSTM cell. And so this idea is that there's some function that represents some forget, which represents how much to forget from the previous cell state. There's a function that represents how much of the current input is actually related to. So we have, again, forgetting from the previous state, a function that represents the current input, a function that represents the current output of the cell, and how the output actually operates on the current cell and the input, and then how the actual cell itself will change. And I think it's really intuitive. If you just look at these last two lines, you feel like this is pretty complicated math. But the idea is essentially we have this idea, we have a cell state, and this cell state is dependent on the forget function. This element stands for some element-wise multiplication. And so we have some forget function which multiplies by the previous cell state, t minus 1, and we add it to the input times the current cell state, which is the c of this little tilde thing, and so we actually get the current cell state as a function of the forget function times the previous cell state and the input and times the current cell state, which kind of makes sense, right? We forget some of what we learned last time, but we also want to retain some, and we also want to incorporate our next decision based on the current input. And then what we do is we have another function for our output. How do we actually determine what the output is? Times this is the sigmoid activated cell state, so essentially just if the activation function, and this is essentially the way that it's kind of negated at the output level. And so I'm not going to go really too much more into LSTMs, and I highly recommend there's two really good papers that I'll leave in the description below, the original paper, and there's a 2017 sort of review, which I think are great resources if you're really interested in getting the LSTM. But essentially, you just really want to understand the idea is it is this sort of sequential time step, and there are functions that represent, forgetting the previous time step as well as incorporating the previous input and how to output that to the next sort of time steps. But the other thing is, all of these sort of operations are differentiable and they can be backpropagated, and that's why we're able to actually use them in the neural network. So these are all very nice kind of functions, and using this sort of way we can kind of make this way that these very smart functions that are able to kind of learn, and essentially we'll feed the words one at a time, and at the end, once we finally have the final cell state, we're able to actually generate the prediction. So we're going to go ahead and look at applying that in the next video. Thank you all so much for watching. As always, I really appreciate it. Definitely help when you help that long short-term memory of YouTube be able to look at a title text, actually be able to understand how to actually go through that as word vectors and see, hey, this guy likes this video and subscribes to this video. He must want to pay this person's rent, because that would really help a lot. And obviously the algorithm sees it. I would really appreciate it. So thank you guys again for watching. See you next time. Bye.